Hello, everyone. So last time we were looking at the method for solving non-homogeneous second-order differential equations. And we saw basically two methods: undetermined coefficients and also variation of parameters. So let's look at a summary of what we did for variation of parameter method. So last time we're trying to solve y double prime plus p of x times y prime plus q of x times y equals f of x. And we assume that, let's say, y1 and y2 are linearly independent solutions of the homogeneous equation. Let's say y double prime plus p of x times y prime plus q of x times y equals 0. Then a particular solution for this equation, particular solution can be written as yp equals u1 y1 plus u2 y2, and u1 is equal to, we derived the expression for u1 and u2. u1 was minus integral y2 f of x dx divided by w of y1 and y2 Wronskian, and u2 was in integral y1 f of x dx divided by w of y1 and y2. And w of y1 and y2, we saw that this is this can be written as determinant y1 y2 y1 prime y2 prime. And it's non-zero because y1 and y2 are assumed to be linearly independent. If y1 and y2 are linearly independent, then w of y1 and y2 cannot be the constant function 0. And therefore, we can divide it by, divide that expression by w of y1 and y2. Now, let's look at an example of applying this method. Example, find the general solution of this equation, 2y double prime plus 18y equals 6 tan 3x. We want to find the general solution of this equation. First of all, obviously, we can simplify this equation a little by just dividing both sides by 2. So let's divide both sides by 2. And then we get y double prime plus 9y equals 3 tan 3x. So right now we have a non-homogeneous equation because right-hand side is not 0. It's 3 tan 3x. And we cannot use undetermined coefficients right now either, because for undetermined coefficients, we had a certain table. And if the function on the right-hand side was one of the functions appeared in the table, then we knew what we could guess according to that table. So for example, we saw that if the function the right-hand side is a sine beta x, then we can use our guess as a sine beta x plus b cos beta x. Let's say if it was a sine, small a sine beta x, if the function in the right-hand side was this, then our guess could be, let's say, capital A sine beta x plus capital B cos beta x. And this coefficient here is generally not same as this coefficient. And same for this coefficient. It's generally not same as this coefficient. So if the function on the right-hand side was something like this, then we could have a guess like this. But in our table, we did not have tan 3x appeared there. So we do not have currently a guess for a function of this form. So for this reason, we will use the other method that we learned, which is variation of parameters. So let me mention here that. So first of all, let me mention about the because we want the general solution. How does the general solution look like? So first, note that the general solution of this equation can be written as y equals yc plus yp. Complementary part plus a particular solution. Complementary part, we can write it as c1y1 plus c2y2 plus yp. And c1 and c2 are constants. And yp is a particular solution which can be found using undetermined coefficients or guessing, or using variation of parameters. And for yp, since tan 3x or tan beta x is not appeared in our table, for undetermined coefficient methods, it's not appeared in our table for that method, so we will use the other method. Since it's not appearing in our table for this method, we will use our other method, which is called variation of parameters. So in variation of parameters, we know that yp can be written as u1 y1 plus u2 y2. So then if we plug back, the general solution can be written as, so the general solution will be y equals yc plus yp. Yc can be written as c1 y1 plus c2 y2. Yp can be written as u1 y1 plus u2 y2. And here c1 and c2 are constants. What about u1 and u2? u1 and u2, I just mentioned the formula for them. This is u1 and this is u2. So u1 is minus integral y2 f of x dx divided by w of y1 y2. u2 is integral y1 f of x dx divided by w of y1 y2. So first we need y1 and y2 because both yc and yp include y1 and y2, the linearly independent solutions of the homogeneous equation. What will be the homogeneous equation here? Homogeneous equation means you have to replace the right-hand side with 0. So first, let's find y1 and y2. So what is the equation? Our equation is y double prime plus 9y equals 0. Then we need the characteristic equation. Characteristic equation. For characteristic equation, I have to replace derivatives here with powers of r. So y second derivative will be replaced with r to power 2. So r to power 2 plus 9 equals 0. And that gives me r squared equals minus 9. This gives me r equals plus minus root minus 9, which is plus minus 3i. Plus minus 3i, so y1 can be written as sine 3x. Y2 can be written as cos 3x. If you remember the procedure for finding linearly independent solutions, if we have two complex roots for our characteristic equations, like alpha plus minus I beta, then the solutions corresponding to those roots will be e to power alpha x sine beta x and e to power alpha x cos beta x. Here alpha is 3 and beta is alpha is 0 and beta is 3. So our solutions will be e to power 0x sine 3x and e to power 0x cos 3x, which means sine 3x and cos 3x. So these are the solutions for the linearly independent solutions for our equation. Now, u1 will be how much? So u1 will be minus integral y2 f of x dx divided by w of y1 and y2. And what is w of y1 and y2? Let's find it. W of y1 and y2 is determinant of sine 3x cos 3x, derivative of this guy, which is 3 cos 3x, derivative of this guy minus 3 sine 3x. So then I have to multiply this guy with this guy, minus 3 sine squared, minus 3 cos squared. Sine squared plus cos squared is 1. So this will be minus 3. Minus 3. So then this will be equal to minus integral of y2, which is cos 3x, times f of x. F of x is 3 tan 3x divided by minus 3. W is minus 3, so then this will be dx. So this will be 3 cancels, minus cancels. So I will have integral cos 3x times tan 3x. Tan 3x means sine 3x divided by cos 3x dx. So then this cancels with this. I'll be left with integral sine 3x dx, which is minus 3 cos. So it will be cos 3x divided by minus 3. Because derivative of cos 3x will be minus 3 sine 3x, then minus 3 over minus 3 over 1. I'll be left with this. I don't need to include plus c here because I am just looking for one antiderivative for this function here. So I can just set the constant to be 0. And similarly, let's find u2. u2 is equal to integral of y1 f of x dx divided by w of y1 and y2. Then this will be integral y1 is sine 3x times 3 f of x is 3 tan x. 3 tan 3x divided by minus 3 dx. Then this will be minus integral sine 3x times tan 3x. Tan 3x means sine 3x divided by cos 3x. And then this is minus integral sine squared 3x divided by cos 3x. So we have sine squared 3x divided by cos 3x. Now sine squared I can write it as 1 minus cos squared. 1 minus sine squared 3x with 1 minus cos squared 3x. So let's replace it. Minus integral 1 minus cos squared 3x divided by cos 3x dx. Then this will be minus integral 1 over cos 3x minus cos 3x dx. Then this will be minus integral secant 3x minus cos 3x. Now, what is antiderivative of secant? Antiderivative of secant is ln secant plus tan. So ln, so minus ln absolute value secant 3x plus tan 3x. But then I also need to multiply it with 1 over 3 according to the chain rule, because when I differentiate this function, like ln secant t plus tan t will be secant t, but times derivative of t, which is 3. So I have to divide times 1 over 3 or divide by 3, so that 3 is canceled out, and I'll be left with secant. This minus comes from this minus. And then this minus times minus will be plus, so plus cos 3x. And antiderivative of cos 3x is sine 3x divided by 3. So this is my u2. And I had my u1 as well. So let's replace back. So substitute back into which equation? See, I had this general solution here. So let me call this equation star. I just needed to find u1 and u2 because c1 and c2 are arbitrary constants, which is generally included in my general solution. And I can find those constants once the initial values are given. But right now the initial values are not given. So my general solution can be written in terms of these constants. So I will have u equals to substitute back into the equation star. Then we'll have y equals c1 y1 plus c2 y2 plus u1. Okay, let me write it u1 y1 plus u2 y2. Now u1 was y1 is sine 3x, y2 is cos 3x. So c1 sine 3x plus c2 cos 3x plus u1 times y1. u1 is this guy here, minus 1 over 3 cos 3x times y1, which is sine 3x, plus u2, which is this guy here, times y2, plus 1 over 3 sine 3x cos 3x, because u2 contains two terms. One term is this, times y2 will be 1 over 3 sine 3x cos 3x. And then this guy here times y2, it's going to be minus 1 over 3 ln sine 3x plus cos 3x times cos 3x. So this cancels out with this term, and then I'll be left with c1 sine 3x plus c2 cos 3x minus 1 over 3 cos 3x times ln absolute value sine 3x plus cos 3x. Absolute value sine 3x sine 3x plus cos 3x. So this will be my general solution. General solution for our equation. All right, let me give you some exercises here. Exercise. Find the general solution of this equation, y double prime minus 2y prime plus y equals e to power x divided by x squared plus 1. The procedure is similar to the previous example. The function in the right-hand side is not appeared in our table. So we cannot use undetermined coefficient method. Instead, we can use variation of parameters. And for that, we need y1 and y2, the homogeneous, the solutions, the linearly independent solutions for the homogeneous equation, where this equation here, will be replaced by same left-hand side, but the right-hand side will be replaced with 0. So then you will find the y1 and y2, the linearly independent solutions of that equation. Once you have y1 and y2, you can find yp as u1 y1 plus u2 y2. And then the general solution, as we saw, will be yc plus yp, c1 y1 plus c2 y2, plus this part, which is yp. So it's similar, only the only difference is that the calculations will be a little bit different because the function in the right-hand side is different than what we had before. And the function in the left-hand side is also different. So that means y1 and y2 will be also different. Previously, we had two complex roots, but here, if you write the characteristic equation, you will see that the characteristic equation has two repeated real root, one repeated real root, which is r1 equals r2 equals 1. And therefore, the linearly independent solutions would be e to power x and x e to power x. So that will be your y1 and y2. So once you have y1 and y2, you have also f of x. Find u1 and u2, and then find the general solution. So I told you the hint how to proceed, but please write down the details, all the details and all the calculation, and try to complete it as exercise. Now the next exercise, find the general solution of this equation, y double prime minus 5y prime plus 6y equals e to power 4x. So part A, by using undetermined coefficient method, and part B by using a variation of parameters method. So see, this equation is a little bit different because the function in the right-hand side is e to power 4x, which is appeared in our table using undetermined coefficient method. So that means for this exercise, we have two options. Previous exercise, we had only one option, which was using variation parameter method because the function in the right-hand side was not appeared in our table. But this function, in the function in the right-hand side, is in the form e to power beta x, which is appeared in our table using undetermined coefficient method. So we can have a guess for our function and particular solution if you want to use undetermined coefficient method. And But we can also still use variation of parameters, because for variation of parameters, the only thing that we need is to have access with to y1 and y2, the linearly independent solutions for homogeneous equation, which is something we can easily find here. So we can still find y1 and y2. We have also f of x, so we can still use variation of parameters because we have y1 and y2 and f of x. We can find u1 and u2 and then proceed. So we can use variation of parameters. We can also use undetermined coefficient method because the function on the right-hand side is appeared in our table. So we have two options to find yp, a particular solution. But the general solution can be written as yc plus yp. Yc means c1 y1 plus c2 y2, and then plus yp. So for yc part, we don't have two options. We just need to find y1 and y2, which is the solutions for the homogeneous equation where right-hand side is replaced by 0. So for yc, we don't have two options. For yc, we just need y1 and y2, which we can find by finding the characteristic equation and then finding the roots and then finding y1 and y2. yc, we will find it that way. But for yp, we have two options. We can, in this example, we can use undetermined coefficient method using the table we explained last time, or we can use the variation of parameters using the formula we derived, which is u1 y1 plus u2 y2, and then u1 and u2, we know the expressions integral like minus y2 f of x divided by Wronskian and so on. Okay, so this example is also similar to previous one. And the example that we did, the only difference is that the function on the right-hand side is appeared in the table. So we in addition to the method that we just did for the previous example, which we can still do a similar calculation to find yp. This time we have one more option, which is using undetermined coefficients. Okay, so please do complete the details as for this example as well as an exercise. All right, now let's look at an application of second order ODEs. So we learned how to solve second order ODEs, whether homogeneous or non-homogeneous equation. Now let's look at applications of each case. The one famous application of second order ODEs is mechanical vibrations, how we can solve the differential equation related to mechanical vibration. So application of second order ODEs, mechanical vibrations. So let's consider a spring. Consider a spring of natural length L. Let's assume that the natural length of this spring is L. We have a spring like this, and the natural length here is L. And we want to attach an object to this spring. Now attach an object with mass M, which will mass M to this spring. Which will extend the spring length. Which will extend the spring length by L units. So once we attach the spring, once we attach a mass M to the spring, the length will be extended by L units. So this will be the original spring L, and then we have the extended one. So still we have this original L, and now it's also extended by L units. So we want to write the basically equation of motion for this mass in terms of time. So suppose that U of t denotes the position of the object at time t. And assume that U of 0 is 0. So at time t equals 0, we assume that the mass is at U equals 0, which we can call it the equilibrium position. And the goal is to find or to set up the ODE for U of t and solve that ODE to find U of t. So see, once you attach the mass, there will be some equilibrium position, right? So we are assuming that this is the equilibrium position and this is at U equals 0. This is the equilibrium position, which happens at t equals 0. And then once you apply some force here, external force, or if you again change the position or extend it further, let's say if you extend this spring further, then you will have some vibration, and this position of the mass changes with time. We want to find the ODE related to this oscillation, and then find U of t, the position of mass at time t. Okay, now that we want to set up the ODE, we also need to choose a direction as positive direction. Here we'll choose the downward direction as positive direction. So let's say this is the positive direction here. And to set up the ODE, we will write the Newton's law. We'll write the Newton's law for this object to set up the ODE. To set up the ODE, we write Newton's law. So what does Newton's law tell us? So it tells us that MA is equal to the sum of all forces, total force. Now A is the acceleration, which is second derivative of u. So then we can write mu double prime equals sigma f. Now what are the forces that are applied to this object? So the forces applied to this object are, so first of all, we have gravity, obviously. Gravity is in downward direction, and downward I assume is positive. So F1 equals the gravitational force, which is mg. And then we also have force applied by the spring itself, which we can measure it by Hooke's law. So F2, let's say, equals Fs, which is going to be minus K times L plus U. See, at time t, because at 0, we are assuming that U is 0, but I'm writing the Newton's law at any arbitrary time t. At time t, arbitrary time t, U may not be 0. So let's say if U is this much, let's say, if you have, if the object is displaced from the equilibrium position by U units, so it's already L units here, and then U units here. In total will be L plus U, and L plus U will be in the upward, the opposite direction, which means upward direction here. And I'm assuming that downward is positive, so upward will be negative. So, and the total displacement is L plus U. And if I assume that the spring constant is K, then I can write the, by Hooke's law, I can write the force applied by this spring as minus K. Minus is because it's in upward direction. K is the spring constant, and L plus U is the total displacement. So then we'll have, so let me write down here that here K is a spring constant. L plus U is total displacement. And minus is because the force is applied to upward direction. And F2 or Fs is the force applied by the spring and can be computed using Hooke's law. So this is a force that we have here. Now for equilibrium position, in equilibrium position, U is 0, right? So this U is 0. There's no additional displacement from equilibrium position in equilibrium position. So U is 0. And then what will I have? Then I can say that the total force. So then I'll have mg minus KL equals 0. Because in equilibrium position, the object is at stationary, so it doesn't move, so it doesn't have acceleration either. So MA becomes 0. Now MA is total force, and in the equilibrium position, I have one force downward, which is gravitational force, one force upward, which is minus KL, because U is 0 there, so minus KL. So then I need to have mg minus KL equals 0. So this 0 here is because by Newton's law, this is supposed to be MA. But if the object is at stationary, it doesn't move, it doesn't have acceleration, so MA becomes 0, and this is the total force which must be 0 as well. So then that gives me mg equals KL. Or I can find K as mg over L. The spring constant can be found this way as well. So this is the second type of force that we can have. And now what other type of force can we have? We can also have a damping force. So remember, I'm listing the types of the forces applied to the object. So we can have gravity. We have gravitational force. We have the spring force. We can also have damping force. If we assume that the friction, we have some friction, then we will have also damping force. So damping force. This is the force caused by friction. And can be written as Fd, damping force, equals minus gamma V equals minus gamma du to dt, or minus gamma u prime. And what is gamma? Gamma is a constant called damping coefficient. So it depends on the material. Depends on the material. And in practice, we have friction as well. So we have damping force. And in physics, it can be shown that the damping force can be written as minus damping coefficient times velocity. And velocity means the velocity here means the first derivative of u. So, or u prime, in other words. So where I can say here, where gamma bigger than 0 is called the damping coefficient. Damping coefficient. So this is the third type of force that we can have. And finally, the fourth type of force that we can have here is external forces. External forces. So we may want to apply some external forces. The previous three forces were all internal, like internally applied in the system, like by gravity or by spring or by damping or by friction, basically. And external forces, we may decide to apply some forces externally. So this one, let's call it F4 or F of t, which is generally a function of time. And if F of t equals 0, and then we call the oscillation free oscillations or oscillation. So we have these types of forces that we can have applied to the object. So now we are ready to write the Newton's law. So in our case, the Newton's law can be written as follows. So MA, which is MU double prime, equals total forces, sigma F. So we have mg downward minus k times L plus U upward, and then minus gamma U prime upward, and then plus F of t, which could be any external force. So this is our F1, gravitational force, F2, spring force, F3, damping force, F4, gravitational force. So MA should be the addition of all these forces. Now, if I simplify, I can write mu double prime as mg minus kl minus ku minus gamma u prime plus f of t. And now mg minus kl, we know it's 0. So mg minus kl is 0. Equal to 0, C above. So I will have mu double prime equals minus ku minus gamma u prime plus f of t. And if I take the first and second term, the right-hand side to left-hand side, then I'll have mu double prime plus ku, or let me write the other term first, plus gamma u prime plus ku equals f of t. This is the equation of movement for this oscillation, movement of the object in this oscillation. This is the ODE for the position function u of t for the object. Now, what initial conditions should I assume with the following initial conditions? So I can assume that so this is a second order ODE. So we need two initial conditions in order to find a unique solution for this equation. So u of 0, the position at time equals 0. I can assume that it's u0. This is the initial displacement. Initial displacement from the equilibrium position. And also u prime of 0, I can assume that this is, let's say, v0. This is called initial velocity. The velocity at time equals 0, v0. So we have two initial conditions and one second order linear ODE, which can be homogeneous or non-homogeneous, depending on whether f of t here is 0 or non-zero. This f of t, if you remember, is the external force. It might be 0, might be non-zero. If it's 0, then we will have a homogeneous equation. If it's non-zero, we will have a non-homogeneous equation. Now we can find the solution for this ODE. Now that we have the ODE and also the initial value, now we can find the solution for this initial value problem. Now we can find the solution of this initial value problem. And I'm going to consider different cases or different scenarios. And in each scenario, I will find the solution for this initial value problem.